All right, we just finished with radiometric dating. Let's get into this geological time scale, also known as the GTS, if you ever happen to see where it says GTS. All right, so anyhow, so here we have, this is a very nice picture. It gives us the longest periods, or I shouldn't use the term period actually. The longest amount of time are called eons, and you can see they're basically broken into the Precambrian and then this uh, Phanerozoic. All right, so the Phanerozoic is broken into the smaller parts called eras or eras. Era is the way I usually pronounce it. But notice even the Precambrian is broken into um, the Hadean and the Archean and the proto. Sometimes it's hard to say these. The Proterozoic. All right, so the Proterozoic. All right, and now just to all right, and then let's continue this. So this eon that by the way that we're currently in is broken into the Paleozoic, the Mesozoic, and the Cenozoic. The Cenozoic is further, and then you divide these into periods. All right, so the here, let's go back here. So there's six. So let's see, 1, 2, 3, 4, 5. So yeah, so there's six periods in this era of the Paleozoic. So we'll talk about each of these in further detail. Then we get to the Mesozoic. This is kind of the middle part. I guess I should mention this. The Precambrian time is incredible. This is an incredible amount of time. Like this is like 90% of the Earth's history. Like when you consider, of course, the Earth is 4.6 billion years old. This amount in this more the common eon that we're now in. This is less than half a billion years. So 500 million years and well, a little bit more than 500 million years. And that's, we concentrate on this because we have a lot more records of this particular time, these eras, and these periods. All right. So anyhow, the eras are divided. So I just was mentioning the Mesozoic is the kind of the middle era. This is the time of dinosaurs, as a matter of fact. You can see that with, you can always tell that with the Jurassic. But there was actually three parts, there are three periods that the dinosaurs existed in. The Mesozoic is broken into the Triassic, the Jurassic, and the Cretaceous. The end of the Cretaceous is that's when the Cenozoic. So this is the time of mammals. Right, of us really, and really we're in this epoch. All right, so these are the periods. You break these down into the tertiary and the quaternary, and then each of those is broken down into smaller epochs. The Pleistocene. And so forth, right? We'll go through each of these, but this is the Holocene is the modern. That's the modern era where humans come along, and all right. So let's get more into that. So specific dates, of course, are used with radiometric dating. Other than that, of course, we have to use relative dating. All right, so the Precambrian ranges from the creation of the Earth, 4.5. It's actually closer to 4.6 billion. 4.6 billion years ago to a little more than half a billion years ago, 543 million years ago. And you might wonder, what happened then, right? Why did we pick this particular time? And there's a good reason for this. Okay, when we come out of the Precambrian, this Precambrian era. Oops. So when I'm sorry, this eon. When we come out of this, then there's like an explosion of life in what's called the Cambrian period. Sometimes it's even called the Cambrian explosion. So we'll get to that shortly. Okay, so but I want to go through each of these: the Hadean, the Archean, and the Proterozoic. All right, so. And again, this is not at all to scale. I want everybody to look at that. I mean, these over here are in hundreds of millions of years. These are in billions of years, right? So it's just that we just don't have a lot of information about this. I mean, there's not even rocks that survive that go back, 4.5 billion years ago, right? Because anything that was that old has undergone, either metamorphism or actually turned back into magma, right, through the rock cycle. Anyhow, so in the very early days of 4.5 billion years ago of our planet's existence, there's a lot of volcanic activity. There's actually really strong evidence of meteor bombardments, but we do feel that there was life. In fact, there's evidence of life in what's sometimes called the blue-green algae, also known as cyanobacteria. That it just gets its name from the color that it is. And these are not hard-bodied organisms. You don't really see a lot of fossils from this time because to create fossils you kind of need these harder shells that hadn't happened yet. And the atmosphere is extremely primitive, as we're going to see. Most of the atmosphere was carbon dioxide back then. It's basically the stuff that comes out of the volcanoes: carbon dioxide, sulfur dioxide, water vapor. These are things that dominate the Earth. There's even methane. I'm sorry, not methane, not yet. Anyhow, all right. So when the Earth first formed, remember, you don't even have a lithosphere. The Earth is just this molten rock. And that it takes a while for that to cool down in this Precambrian time, this Precambrian the eon that is the Precambrian. All right. So the one thing that I want to mention about the Hadean time, as it says here, there was lots and lots of bombardment from meteors. In fact, in astronomy, the astronomy of our solar system, the history of our solar system, we talk about what's called the late heavy bombardment, which is basically the solar system. When the solar system formed, the planets that we now know, the 8 planets that exist as we know them and where they are, that was not the situation in the early solar system. The planets moved around. In particular, Jupiter moved around, and when Jupiter did this, it caused the material that is between Jupiter and Mars, which collectively that material is called the asteroid belt. It flung, because of the motion of Jupiter changing positions in the solar system, it flung a bunch of material towards the inner part of the solar system, which is, of course, where we are. And that's often called the late heavy bombardment. But there was one special thing that happened. that is still in evidence today. It's observable. In fact, you guys are doing your project on it, right? And so what happened, and we'll explore this in a little bit more detail when we get to the chapters on astronomy. But what happened during this time is that an object, and we estimate the object to be about the size of Mars. It's, of course, not Mars, but there was another planet. In fact, we think there were dozens of planets in the early solar system, and really the 8 that we have now are the survivors. So what happened to those planets that were out there orbiting our sun? Some of them collided. Some of them ended up being flung out, outside of the confines of the sun, the gravitational attraction of the sun, and got flung out into the galaxy. And some of them just ended up being flung in towards the sun, and then the sun basically just evaporated it when it got close enough. All right, but this one collision that I'm talking about, of course, is this Mars-sized object, which, by the way, does have astronomers love to name stuff. So it's actually called Theia. This object that hit the early the early Earth, and what happened is when it hit, it hit Earth on a kind of an off axis. I should have a picture of the Earth, but it hits the Earth. Hold on, All right, so this is collectively called the giant impact theory. Let's look at this picture right here, because this kind of shows it. So this is the early Earth during the Hadean period, the very beginning of the Precambrian era. And I'm sorry, not era. And Theia comes in and hits the Earth at a glancing angle, and that's actually turns out to be really important, because that gives the Earth a tilt with respect to the sun, and so this is the impact of Theia. This is an artist rendition of it, of course, and the material that was this little tiny planet roughly the size of Mars. Coalesces around the Earth. It takes a certain amount of time for that to happen, and then eventually becomes our moon. Right? That's the idea. And in fact, this idea was scorned at first. People didn't think that's how the moon was formed. But now more and more evidence has shown that this is indeed the situation. Here, let's see if there's any better pictures. So there's another picture that kind of shows. I mean, it did. It would have devastated if there were any life on the early Earth. It definitely would have devastated everything. It would have turned all the, if there was any kind of solid rock, it would have turned it all into molten rock and turned it back into liquid. So there's some more pictures. I mean, remember, it's always artist rendition of what's going on. But here, if you look over here, you can't see this very well. Let me get move this a little bit. Oops. Let's move. You guys can see this. All right, so there you can see that a little bit better. So this is, the impact. Again, it's Theia hits. It's an off center. Then as it coalesces, this thing forms our moon, and of course that causes the Earth to tilt by 23.5 degrees. That 23.5 degrees is very stable, actually, because of the orbit of the moon. The orbit of the moon maintains that stability over time. And of course, this tilt, that 23.5 degree tilt, is what gives us our seasons. All right, so that's actually really important to us.